Hi everyone, I will talk about the concept of integral in this video. Integral concept has been started to appear in the history by the motivation of finding area. This kind of, please firstly focus on this kind of shapes, which is an integral, triangle, and a confused shape. But what is common in these shapes? All of these shapes are surrounded by lines, straight lines. When you try to find this kind of shapes area, it is enough to think on classic geometry, Euclidean geometry. When you try to find the area, you must measure the number of unit squares in this rectangle or in the area, in that area. In the rectangle, it is enough. For example, in this rectangle, 1, 2, 3, and 1, 2, 3, 4, 5, 3 times 5, 15 unit square exist in the area. And this shape, the triangle, you can easily complete this triangle to the rectangle, and you can understand that the area of this triangle is the half of a rectangle. And this kind of mixed shapes, you can complete these shapes to a rectangle or triangle or trapezia, something like that. And so you can find the area again. You can find the number of the unit squares exist in the area. But when you face to face this kind of shapes, something is changing, because the unit circles cannot be found easily in this kind of shapes, and we need to try a different method to find these shapes. In mathematics, if you place this shape into a coordinate system, you can obtain regular region represented by a function, and you may try to discover or explore a way to find the area of this region. And then the method of finding the area of this kind of region can be applied the other part of this region, as thinking similarly. Let's go on by this application. I prepared this application before. This curve is represented by this kind of function. Of course, this function can be changed. And then let's think about on how can we find the area of this region. I will introduce you a method from Archimedes called exhaustion. Exhaustion means divide the region like that, then think about this part of the regions some regular geometric shapes. For example, it may be a trapezia or rectangle. Of course, trapezia is the first which we may think, but if you decide to create rectangles like that or like that, never will change when you increase the number of the partitions. Because the partitions, when the partitions are limited number, there are some difference from the actual area. But when you increase the number of partitions, the difference from the actual area will exhaust. Because of that reason, this method called exhaustion. Let's decide one of the choice. Show the numerical entities, and let me explain how can we evaluate the sum of the rectangles. Here is the x a is 0.859 now, and b is 3.55, and a plus b minus a over n times I will be here, and the image under the function, this function, will be here. So, and then product by the b minus a over n. B minus a over n, the difference in the x called delta x, and add all production. So you will obtain this kind of result. When you increase the number of partitions, the result will approach a constant value. This is the area of our actual area, our actual region. But something is important here. After this approach, you may say that this result is an integral, is an area. But I will show you a difference. What is the difference here? In this entity, I calculated the area of rectangles geometrically, and here I calculated the rectangles by using exactly delta x times delta a plus I delta x of f of a plus I delta x. And there is a difference here. What is the reason? And here, I am started to understand. Because this is the because of the function, when your function is completely under the x-axis, the result is negative of the actual area. And when you obtain this kind of region, your result will completely different from the actual area. So because of that reason, we will call this concept a special sum instead of area. This special sum is called integral. This syntax coming from continuous sum syntax, and you will add all fx between a and b times dx. Now we have a new concept, finding area of the region surrounded by curves, and let's apply this method to some specific region. For example, let's choose fx equal to x, a equal to 1, and b equal to 2. Fx is equal to x, a is 1, a is 1, a is 1, and b is 2. Okay, and let's increase the n. Of course, this dynamic application is just to create an idea, an intuitive approach. This is not exactly the limit, because the number of partition is 1000 here, and 1000 is a little number when you compare by infinity, because our concept is here. You must take the limit while n goes to infinity to reach the exact result. But I prepare a calculation for you here. Of course, I will show you in seconds in this video. You can pause the video and examine how the limit calculated. The result is 3 over 2. This is also a regular geometric shape with surrounded by straight lines, and this is a trapezium, so you can also calculate the area by using trapezium's area formula, and you will obtain the same result. Let's try another problem. Let's make the function x square now. When you make the function is x square, you will obtain this kind of region, and the result is 2.3 blah blah blah, and the calculation is here, and the result is exactly 14 over 6, which is equal to 2.33333. Again, our method worked here. Let's think on this kind of function. When you try to calculate these functions integral between -1 and 1 by using this limit method, it will be so hard. But let me show you the result by using this application again. Square root of my 1 minus x square, and a is minus 1, b is 1, b is 1. So as you understand and observe, square root of 1 minus x square between minus 1 and 1 represents a semicircle, and you can also understand a semicircle's area whose radius is 1 is pi over 2, which is here. But how can we calculate with this function and this kind of limit? It is so hard. At this time, we need to discover a new method to calculate this integral, to calculate this operation, which we called now as an integral, and which we show a new syntax here, and this will take us fundamental theorem of calculus. I will explain fundamental theorem of calculus in forthcoming videos, one of the forthcoming videos. Thank you for watching.